Don't know the answer? Ask the Naked Scientists.
Hello and welcome to this week's Ask the Naked Scientist with me, Sue Marchant, and Chris Smith. All right, well, how is the world of science?
There's some wonderful stories out there this week, and this one particularly caught my eye because obviously we heard a lot about climate change and things before Christmas because of the Copenhagen meeting, and researchers are looking for ways in which we can fulfill our energy needs around the planet in a more sustainable way. And so, of course, green energy is top of a lot of people's agendas. Now, we're not just talking about things like wind power, but we're talking about putting energy into a form that is useful. And the form that we find very useful at the moment is, of course, oil. But oil is bad because it's a fossil fuel, and that means that it's a stored away form of CO2, which when you burn it liberates the CO2, it goes into the atmosphere, and it could contribute to climate change and global warming and greenhouse effects down the line. So we want to try and find more sustainable ways of doing things. One way is to try to use plants as a source of energy for turning into things like oil, and this is where the whole biodiesel and bioalcohol comes from, bioethanol. But the problem is that these processes take out of useful production land that we need to grow crops. People are very worried about where the land is going to come from to grow crops to feed an increasing world population in future. And to turn farmland into land that's growing energy crops is bad news. So we need a better solution. And there's a group of researchers in California. This is the University of California, Berkeley. They've got a paper in Nature this week, Jay Kiesling and his colleagues. And what they set out in there is a way of turning our good old friend, the gut bug E. coli, into a producer of biodiesel. And it's a very elegant paper. What they do is to build on the fact that every living thing, most cells, need to have oils in them anyway. All of the cells in our bodies have a cell membrane. And these membranes are very oily. That's how they work. And so you need to be able to make oils in your cells in order to sustain those membranes. So by manipulating the metabolism that's naturally in these bacteria, they are able to divert the production of these oils into a pool that could be used for other chemical reactions. So they added a gene that did that. Then they borrowed a gene from a plant that would chop these oils up into convenient lengths of chains of carbon atoms that mimicked biodiesel. Then they added an enzyme that would enable the bugs to make their own ethanol, alcohol, and then they added another enzyme that would link the alcohol to these fats that they were making to make ethyl esters. And this is exactly what biodiesel is. And very quickly they were able to produce bacteria, E. coli, that when incubated in a sugar solution will produce biodiesel, and at large amounts too. Now, this is just the start, and what they do say down the line is we don't want to be feeding bacteria on sugar. We want to actually be giving them our rubbish that's in our dustbins and letting them break that down and turn into biodiesel. That's not so far into the future because there are various enzymes that could also be added to the bacteria so they could take plant waste, the kernels of sweet corn, the cores of your corn on the cob, all that stuff we throw into landfill but which is full of carbon, and they could turn it into what we are referring to as biodiesel, which is definitely the way forward because bacteria don't draw a wage, they're cheap, easy to grow, you can put them in big reactors, don't take up much space, but they will yield very large amounts of potential fuel feedstocks and other chemicals that are great for the chemical industry without having to use fossil fuels.
That is fantastic, just amazing. So we'll all be composting well into the future, I think, won't we?
Well, this is the future. This is the way it's all going. And the use of what's becoming increasingly known as synthetic biology, coupled with a better understanding of genetics and how we can build on what nature has given us and bring that material and that science into one place and put it into, say, a bacterium and use that to produce things for us so we don't have to damage the world. That is the way it's going. We're going to see this increasingly in the future.
Let's go to the phones first and welcome Tony onto the airwaves. Hello, Tony.
Good evening, madam.
Good evening. You're through to Dr. Chris. What's your question?
Well, do you think we'll ever get Smellovision? In other words, I'll be able to somehow other have a cassette in your set that they can work out so you get the sort of smells of wherever you are.
It would actually be very simple to do this, Tony. If you've ever been to one of these museums that seeks to recreate the past for you and show you how smelly people were in the past, and Diana O'Carroll, who's our resident archaeologist on The Naked Scientist, pointed this out the other day when someone actually phoned into The Naked Scientist and said, were people just less smelly historically in medieval times? Because the standard of hygiene then was absolutely appalling. And if you look at people today who get pretty whiffy, and most people do wash most of the time, what was it like 500 years ago? The answer was people just reeked. But the bottom line is, she was pointing out that we can recreate a lot of those smells when you go to the Jorvik Centre and things, because we know what the chemical fingerprints are that make things smell the way they do, and there are various chemicals that you can make that smell similar, but which are safe, and so you can experience what it would have smelled like to travel through Rome and York, for example, which is what the Jorvik Centre does. Well, it wouldn't be that difficult to beam alongside a TV signal, especially with the big bandwidth that's now available, the way that modern data is being deployed, an associated signal, which would also be a smell fingerprint. And you could feed that into some kind of chemical box which had a cocktail of chemicals in it, which could release those or diffuse those into the room to create an olfactory experience. It'd be like four-dimensional TV, wouldn't it? So you get the sound, you get the light, you get the colour, you also now get the smell. Thing is, I think it would depend on what sort of programme you're watching. I mean, it'd be great if it was a cooking programme, really nice, delicious smells, you could experience the food. But just imagine if it was a programme all about how sewage works. Would you really want that coming into your living room? And then people would walk in to visit you, and they'd come in and they'd think that you'd made that smell. And you'd have to explain, it's the television. No, it wasn't the dog. This time it was the television.
Tony, thank you very much indeed.
Lovely, very interesting. Thank you.
All right, you take care. Bye-bye.
Bye.
Let's go to another question now. This time we're going to a question from Mike. When we are under stress, our body heat rises dramatically. Hot under the collar is the ultimate effect. Is hot under the collar, is it the ultimate effect of this spontaneous combustion? Chris?
No, we don't think so. The reason that body temperature rises during times of stress is because metabolic rate goes up. Metabolic rate, in other words, how fast you burn chemicals in your body and turn them into heat and other products, that determines how much energy you've actually got to try and get rid of. And we're continuously doing that anyway because we're warm-blooded. The things that really generate heat are muscular activity, which is why going for a jog or running up the stairs puts your body temperature up. But when you get stressed, the body produces large amounts of adrenaline and other stress hormones, and these augment metabolic rate. They put your metabolism up, so therefore you do tend to feel hotter. That's partly it. But the main point about spontaneous human combustion is it's not proven, but there is a theory. And the theory is that there's something called marsh gas. If anyone ever recalls hearing the myth of Will-o'-the-Wisp, if you go out on the marshes, you sometimes see these flares of light. And there are gases which are derived from phosphorus, the chemical. These are things like diphosphanes, which can be produced by certain bacteria which live in the marshes. Those bacteria also produce methane and other potentially flammable chemicals, and hydrogen. So what scientists think is that what Will-o'-the-Wisp is where a bubble of gas comes up from the marsh. The marsh sort of goes burp, and it releases a blob of methane and hydrogen and some of this diphosphane. And diphosphane spontaneously bursts into flame. And this ignites the gas and makes a big flare. And that's what you see as Will-o'-the-Wisp. The same bacteria with the same abilities to make these kinds of gases do occasionally exist at low level in the human intestine. So one suggestion is that someone who has these bugs could set fire to themselves by doing a fart that spontaneously ignites. Very rare, pretty unlikely, but not impossible. And the reason the body then burns is because the clothing acts as a wick, and the heat from the burning, initially of the clothing, melts body fat. And because fat is just oil, it's just like setting fire to your chip pan. And this soaks into the clothing, which wicks up the melting fat, and that generates more heat, which liberates more fat, which soaks into more clothing, vaporizes and burns, and so the whole person sort of uses their own body fat to burn themselves away. Sounds a bit of a tall order. There's no decent medical evidence this is what happens, but that's the best biologically plausible mechanism that scientists can come up with to explain it.
Very X-Factor. Thank you for that. Let's go to the phones once more. This time we've got Alan on the phone. Good evening, Alan. You're through to Dr. Chris.
Good evening. Over the years, my children have had various illnesses like chickenpox, measles, etc. And whenever they've had that, then following straight afterwards when they're over it, they then become simply more capable, more intelligent, more able to deal with the world in a more adult way. And now it seems that my grandchildren appear to be doing the same thing. Is there any biological reason why this should happen?
Well, I'm not aware of virus infections boosting intelligence, but there's an increasing school of thought which is showing that getting infected with certain viruses definitely trains your immune system, not just to defend you against that virus in future, but to defend you against other infections. The example given is of the members of the herpes virus family. Mm-hmm. Herpes is a big family, not just the viruses that cause cold sores, but also Epstein-Barr virus that causes glandular fever, and another virus called CMV, which causes cytomegalovirus, CMV, a sort of EBV-like infection. And what scientists have found in the last few years is if you do this in mice, we don't know in people yet, but there are mouse equivalents of those human infections, and if you infect mice with those infections and then let the mice recover, and then you challenge them with other nastier infections like plague or listeria, mice that have been pre-infected with these members of the herpes virus family are much better able to fight off the bacterial infection than animals that have not been pre-infected.
Yeah.
And when the researchers make measurements on various immune signalling hormones in these mice, they find that the animals that have been pre-infected with these herpes virus family members make a much better immunological response to the bacteria than immune-naive mice. And one suggestion is that because we have evolved to be infected with these viruses, because they've been infecting us for millions of years, basically what the immune system has done is to use the fact that these viruses are very, very closely related to us now because they've evolved to just infect a single species on Earth. And the immune system relies on some factors which are genetically encoded into the virus to basically prop up the immune system. It's almost like some immune functions have been put into the viral DNA, so the body almost needs to be infected to function normally. Now, I'm not aware of this affecting brain power, but certainly it can infect, on the basis of those experiments, your immune system's power. It may well be that they're making you generally healthier, and therefore you're not catching as many things as you would do normally once you've had certain infections. And worth bearing in mind that chickenpox is also a member of the herpes family of viruses.
Oh, I didn't realise
and therefore it is in some way perhaps tweaking the immune system. So the reason you see this apparent increase in intelligence is because there is less going on in terms of other illnesses in that person once they've got this immune boost, and therefore they're spending less time ill, so they've got more energy to put into thinking.
Right, thank you very much.
You're welcome, Alan. Thank you very much.
Bye.
Thank you. Bye-bye. If you're enjoying Ask the Naked Scientist, then you might like to check out The Naked Scientist, our regular roundup of the world's best science. Each week we take a look at the latest science news, talk to top researchers working at the coalface of discovery, and also get our hands dirty with a science experiment that you can join in with too. So make it a date and prepare to strip down science on the web at nakedscientist.com/podcast. All right, well, let's go to the phones once again because we've got Mark on the line. Hello, Mark.
Hello, Sue.
Now then, what have you got for us tonight?
I've got a couple of questions, if that's all right, or time limiting. The first question I'd like to ask Dr. Chris, the first meteor shower I saw was back in 1988. Could Dr. Chris ask me why they come round so frequently? Where do they come from? You know, do they come in waves?
Indeed, yeah, hi.
Hello, Dr.
The reason that this occurs is because the Earth has an atmosphere, and as it travels through space, it's doing something like 60,000 miles an hour on its way around the Sun. It takes 1 year to go all the way around the Sun, of course. That means that the Earth moves into the path of other objects in space in our solar system, and there are lots of them. There are lots of tiny specks of dust and rock particles and things. Many of them come from comets that pass by. So as a comet goes streaming through, comets are just what are called icy dirt balls. So they're a mixture of ice, water, mud, rock, loosely held together. And as they stream through the solar system, they leave behind a tail because they get warmed up by the sun, and this causes partial melting, and bits of loosely bound material get left behind. And as a planet, including the Earth, goes through the path of the comet, that means that those bits of debris and dust left behind will enter the atmosphere of the planet. That means they'll hit the planet doing perhaps 60,000 miles an hour, in some cases up to 70 kilometres a second as they go through the atmosphere. And that at those sorts of speeds, it's like slamming into a brick wall. So the frictional effect is huge. And this vaporises the particles very, very quickly. And as they vaporise, they give out light. And that's the light show you see.
That's the light
Some of them
show,
are sufficiently big to make it down to Earth.
Yeah.
But the reason they come frequently and they come seasonally is because the Earth goes around the Sun in a stereotyped orbit. We know the path of the Earth.
Yeah.
And because these comets also have a stereotyped orbit, the Earth will periodically cross the paths of these comets. The one that causes the Perseid meteor shower that comes in July-August, for example, that's a comet called Swift-Tuttle. And when we cross the path of that comet, we get all the debris it's left behind, and that comes every summertime.
So that's why we get that regular. Have I got time, Sue, to ask one more question?
Very quick one then, Mark. Go on, as it's you.
It's to do with animals. It's a lot of vets use a drug called N99, which is supposed to be about 1,000 times more powerful than morphine. And they seem to use that same drug when they want to dye any size animal, from rhinoceroses, elephants, down to small little deer. Why is it that that drug is so poisonous to us when they can use it on creatures? I mean, apparently just a scratch or the tiniest drop in your eye and you have to carry the vaccine.
Well, the reason is that body fat and body mass does enter into the equation a bit, because the volume of distribution, how big you are and over what kind of volume you distribute a drug does make a difference. But also species makes a very big difference. And some drugs are much more active against some animals than other animals. The way a drug works, and especially an anaesthetic type drug, is that the chemical that is the drug interacts with some sort of thing called a receptor, a docking station, which is a structure which the drug fits into in the same way that a key fits into a lock.
Yeah.
Now, as you know, you can get skeleton keys, which are not made for all locks, they just happen to fit all locks. Some keys will therefore fit other locks better than others, but skeleton keys can open any lock, but they'll fit some locks better. It's exactly the same in nature. If you make a drug which locks onto a receptor, say in an animal, and blocks that receptor and makes the animal feel sleepy, it might bind to that receptor slightly less tightly than the human equivalent. So when you put the stuff into a human, it binds to the receptor so well because the receptor is slightly different chemically in the human compared to the animal, that therefore it's like the key fitting the lock really, really, really well and then jamming itself in there so well it won't come out.
I see.
And so you end up with differential effects of drugs. And in fact, you see the same thing in different humans. The same drug does not affect everybody the same way. Scientists, doctors are beginning to recognise now that, for instance, if you take drugs used to treat blood pressure, there are some drugs which, if you give them to a white person, won't work as well as if you give them to someone who's African, Caribbean or African. There are other drugs which work much better in white people than work better in black people, and that's down to genetics. So if we have differences to the responses of drugs within our own species, it's not really surprising at all that some drugs will be highly toxic to some species and not others, in the same way that you can tuck into chocolate, but if you feed a big enough dose like a Cadbury bar to your dog, it will die.
I see. Yeah, thank you very much.
All right, thank you, Mark.
Thank you very much, Sue.
Bye-bye. Right, Dr. Chris, we have another question here. I don't know whether you know anything about mucus, but an email that's come in from Tad. It was suggested that milk and dairy products make human body produce more mucus. Is that the case, and how does the process work? Do you know?
I've not heard any evidence that drinking milk makes you make more mucus. I have noticed that if I drink a lot of tea, or if I drink a hot cup of tea, that it tends to make my mouth paradoxically drier and stickier afterwards. But then I thought that could be the caffeine, because caffeine potentiates the action of adrenaline being the body's stress hormone, so it makes you feel more stressed, and that will make you have a drier mouth anyway. So I'm not aware of actually any effects of dairy products on mucus production, apart from the fact that there will be fat in the dairy products, and this will make you produce chemicals which help you to absorb fat, but they're not necessarily mucus, that's more bile.
Right, I know that you've had one or two questions that have come into you, haven't they, by email?
If anyone wants to send us some questions, you can write to me. It's chris@thenakedscientist.com. Gordon Cubank did exactly that. He says, why isn't carbon dioxide at ground level? My understanding is that it's heavier than air, so why isn't all the CO2 drifting around at ground level and all the lighter things like the oxygen much higher up in the atmosphere? Well, the answer is it's exactly the same as when you add, say, some drink concentrate to a glass of clear water. If you poured the drink concentrate down the edge of the glass, it would initially sit at the bottom underneath the water because the concentrated sugar solution would be heavier than the water. But given enough time, because when things are at room temperature, the particles in the drink have got energy, and that means they're zipping around all over the place, moving around, bashing into each other. And therefore, over time, those particles bashing into each other and moving around would mix the two solutions together. And eventually, your drink concentrate, starting off at the bottom of the drink, would make its way through the whole drink, and it would all mix evenly to distribute everything. So the atmosphere is not really any different. There is some CO2 in the atmosphere, not very much though. The vast majority of the atmosphere is 80% nitrogen, 20% oxygen and a little bit of CO2. So there's very little CO2 anyway, but the main thing is that heat from the sun warms up the ground warms up the air above the ground and causes it to rise, and this causes a sort of churning or turbulence which mixes the atmosphere up, and so the atmosphere stays very well mixed, which is a good thing, because if all the CO2 did gather at ground level, we'd have a hard time breathing.
Lovely. Right, let's go to our phones once again now, because we've got Martin from St Albans on the line. Good evening, Martin. What's your question?
Right, OK. Basically, it's to try and find out about microwaves, how efficient they are at heating water. Let's say take a litre of water and you heat that up in a standard kettle with the elements, and if you could make the microwaves sort of all go into the water to heat that up, does it consume more energy using microwaves than it does on a standard element in a kettle?
Hello, Martin.
Hi.
Well, let's first of all, for people who are not clued up on how microwave works, explain how that gets energy into food. So that's the first step. A microwave warms up food because a structure called a magnetron, which is usually on the side of the microwave behind where all the buttons are, produces a kind of radio wave of a fairly long wavelength, about 12 centimetres, which is called a microwave, and that wave goes across the microwave, across the interior, bounces off the other side and comes back mapping onto itself to produce something called a standing wave. This is a wave which, if you could look from the side, would look like it was almost standing still. And what that means is there will be hot spots and cold spots. And that's why you need a turntable, because the food needs to rotate through those hot spots and cold spots, because the amount of heating occurs where you have the maximum vibration, and you get a cold spot where there's a minimum vibration. So if you turn the food through that, you get even heating, hopefully. Now, the reason a microwave makes things heat up is because the microwave is a changing electromagnetic field. That means it's a changing electrical field, which makes a changing magnetic field, which makes in turn a changing electrical field, and so on, and it propagates. Water molecules are polarised. What I mean by that is, if you could zoom in on a water molecule, what you would see is a thing that resembled a tiny boomerang with an oxygen atom at the apex of the boomerang, and the two arms would be two hydrogen atoms. And oxygen loves electrons, so it pulls electrons towards itself very hard. It's very what's called electronegative. And this makes the hydrogen a bit plus and the oxygen a bit minus. So when you put that structure in a microwave, because it's polarised with a plus bit and a minus bit, when it sees this electromagnetic field changing, the water molecule tries to change at the same time. And it flips backwards and forwards at the same frequency, or tries to, as the microwave is changing the wave, which in the case of a microwave in the average kitchen is about 2.5 billion times a second. This vibration generates heat, because the water molecules can't keep up. They're being jostled around all over the place, and they get hot. And that heat is then imparted into the food. So microwaves, the frequency that we use for microwaves, is chosen because it makes water molecules vibrate very fast, and that means you get a good heating effect. So that's how microwaves heat things up. If you could get all of the energy in the microwave into the water, it would heat it up beautifully. But in all stages of conversion, there are going to be losses. There are going to be losses when the microwave makes the microwaves from the electricity coming in from the socket in the first place. Some of the microwaves will miss the water when they go through it, so that won't work for a start, and so on. So the microwave, if you just put a cup in it, is going to be less efficient as a way of heating a cup of water than if you put it into the kettle, because in the kettle, this is much simpler. All it's doing is passing a very high current through a fairly good conductor, some kind of copper conductor, which runs at a very high current, generates a lot of heat, and because the element is completely bathed in water, then the water carries away the heat very efficiently and very quickly, and you get a circulation effect, a bit like I was saying with the atmosphere. The ground heats the gas near the sun heats the gas near the ground, and this causes the hot gas to rise and is displaced by cold gas. Exactly the same thing happens with the fluid in the kettle, and you get a circulation which means it's very efficient. The problem is that electricity is not the best way to heat water anyway, because in order to make the electricity, someone has had to burn something at a power station, usually, whether that's a nuclear power station, coal-fired station, whatever. The best actually way to heat water up is to put a pan on a gas ring and make sure you put a lid on it and try and get as much of the energy from the gas into the bottom of the pan as you can.
Okay. Well, thank you very much. Do appreciate that.
Lovely, you're welcome. Thank you very much. Dom in Newmarket has wondered about the signal for radio-controlled clocks. Does it come from a local mast or satellites? I believe it comes from one central place. Do you know anything about that, Chris?
Yeah, I mean, the idea here is that this way you can get a clock and it doesn't have to be manually set. You don't have to worry about it going off. This is very important in things like the broadcast industry, to make sure that everyone is talking to the right time, because if your clocks aren't synchronised, and same thing with trains and buses and things, if the clocks aren't synchronised, then people are driving and working to their own time. All kinds of problems can happen. So that there is a system in place where a clock signal is broadcast. I don't know if it's handed on from one transmitter to the next, because it would have to be a very big transmitter to get to the whole country without handing the signal on, or there being a parallel transmission from a number of different sites. But there is a central signal which is set accurately, and clocks tune into that signal if they're remote controlled or radio controlled, and they synchronise and lock onto it, and then they adjust their time accordingly in order to be appropriately matched to the central time, so there's no risk of them going wrong. And they also update their time on a regular basis, so they check that they're still right and reset themselves every X number of, in some cases, minutes, in some cases hours, in some cases days. But it's a very good way of making sure everyone's on the same time. Yeah,
it's quite spooky when they do it as well, isn't it? Suddenly the hands of your watch start moving. All right, one last question from the email that you've had sent in, Chris. What's next?
Yes, Calvin got in touch, Chris at thenakedscientist.com, and he says, can a virus actually be made from scratch? He points out that in July 2002, scientists from the State University of New York at Stony Brook said they'd built a synthetic polio virus from scratch. How did they do that? Well, the way they did it, it was actually to prove a point more than anything. You can order on the internet little pieces of genetic material to be made for you. So what they did was to send off lots and lots of orders for lots of short sequences of genetic material using the sequence that had been published on the internet for the polio virus, and then they painstakingly stitched back together all of those bits of genetic material until they had the complete genome of the polio virus, which they then transfected, in other words, moved into cells, and the virus then started up and produced virus particles, and they were able to harvest from these infected cells proper polio virus, in other words, virus that we're trying very hard to eliminate and eradicate around the world. And the reason they did this was to prove a point, which is that people are very worried about bioterror weapons and things like that, and all of the viruses which we're most worried about, especially smallpox, the sequences, the genetic sequences of those viruses are published on the internet. So you could, theoretically, rebuild some of these horrible viruses just using sequences that are in the public domain. If you did this enough times, you could build viruses from scratch. And they were showing that this is theoretically possible. It would be very difficult with smallpox because the genetic material that makes smallpox is huge, so you'd be there for a very long time. But technology is moving forward so fast, it's actually not that unfeasible these days. So it was really more a proof of concept and proving a point, but also proving a very important point, which is that someone with perhaps nefarious intent could build nasty viruses, including ones like polio that we're trying very hard at huge expense to eradicate, and are within a gnat's whisker of eradicating now. And you could release that again into the world. So this is why we have to be cautious about this kind of thing.
That's it for this week. Our doctors will be back with me next week for more Ask the Naked Scientist. But don't forget, you can also catch them on the Naked Scientist podcast, which you can find on the Naked Scientist website, www.nakedscientist.com.
The Naked Scientists comes to you from Cambridge University and is supported by the Wellcome Trust, the EPSRC and UK FAST. For more information, look us up online at nakedscientist.com.